Hello and welcome to the start of Unit 2. To start off, we are talking about properties, with intensive and extensive being the first we will look at. Extensive properties are properties or characteristics that do depend on the amount of matter present. So the measurements we see here, mass, volume, and length with height, would all be good examples of this. So the mass of something depends on how much of it you have. If I double the amount of a substance I have, I'm also doubling the mass of that substance. Intensive properties, on the other hand, do not depend on the amount of present. They will be true regardless of how much of that matter you have. So an example could be color. If we think about that copper 2 sulfate pentahydrate that we used in our hydrate lab, it's blue. No matter how much of it we have, it is always going to be blue. It doesn't depend how much we have, so therefore intensive. Density is another example to definitely know as intensive. The density of something, or the way those particles are arranged within a substance, is the same no matter what. If I have a cup of water versus a lake full of water, those water molecules are arranged in the same form or fashion. That mass to volume ratio is the same regardless. Melting point and boiling point are also great examples. Water is going to melt at 0 degrees Celsius no matter how much we have, and it's going to boil at 100 degrees Celsius no matter how much we have. So moving on from there, we have physical properties and physical changes as well. Physical properties are going to be characteristics that we can observe without changing the identity of the substance. So we can tell what color something is. We don't change what it is. When we find the melting point of something, we don't change what it is. Melting is not a chemical change. If we melt water, it turns into ice. It's still H2O. It's still the same chemical. The identity did not change. So melting then would be a physical change because no bonds are broken. We are not breaking chemical bonds in the reactants. We're not forming new chemical bonds again. The identity of that material does not change. So like the melting that we've talked about, or any changes of states, are all going to be physical changes. So if I melt iron, if I sublime carbon dioxide, physical changes or changes of state. Changes in form are also going to be physical changes as well, so that includes crushing, breaking, and dissolving. When we dissolve salt in water, we do not have a chemical change. We didn't change the identity. It's still NaCl. It's still H2O. So here we can see our dry ice subliming again. Remember, subliming is when we go from a solid directly to a gas without passing through the liquid phase. If we look at that little picture there, we can see those red and black carbon dioxide molecules have not changed. Bonds were not broken. We just spread out the spacing in between them, therefore changing the state of matter. Chemical properties and chemical changes do involve a change or possible change of that substance. Chemical properties are characteristics that we can only observe if we might change the identity of that substance. So for example, reactivity. If I want to know if something's going to react with water, I'm going to stick it with water and see what happens. Well, if it reacts, I've changed the identity of that substance. Or flammability. If I want to know if something's flammable, I'm going to try and light it on fire, and if it burns, we had a chemical reaction. Other examples of chemical properties are things' ability to oxidize. When we talk about iron, we use the word rusting for oxidizing, and tarnishing would be when silver oxidizes. Chemical changes are going to have a change in the identity of that material. We break chemical bonds in the reactants, and we form new chemical bonds in the products. So we have a couple examples of that here. We have our photosynthesis reaction where those bonds in carbon dioxide and water have been broken, our atoms rearranged, and we form new bonds in the molecules glucose and oxygen there. Another example of our propane, we can see the pictorial representation of our molecules over there. We started with our gray and white propanes down there, reacted with oxygen in the air. Those bonds were broken. They rearranged to form CO2 and water, which we can see again in that picture looks completely different. We made something completely new. When we have a chemical change, there's a lot of evidence of that, or indicators that we may see. We might have an unexpected color change. So by unexpected, we just kind of mean if it doesn't fit within like your normal idea of the color wheel, it was probably unexpected and real chemistry happened there. If you mix together yellow food coloring and blue food coloring, we know it's going to turn green. That wasn't a chemical change. We might also see bubbling and bubbles coming out. That would be a formation of a gas. If we form a solid, that is called a precipitate. So a precipitate is when we have two aqueous solutions reacting together to form a solid. We might get a new smell or a new odor. And also energy changes. So a reaction might release heat. It'll feel hot or warm. Or it might absorb heat. It'll feel cold. We can also have energy changes in the form of light and sound being released. So if we think of like an explosion, we have light and sound being released in the form, or energy being released in the form of light and sound. That's an energy change. So whenever we do have one of these chemical reactions, we can describe that in a few different ways. And you do need to be able to convert between these different forms. The first form is what we're probably the most used to seeing, and that's in a formula or in our equation where we have all of our different chemical formulas in there with the state of matters, reactants, yield, our products, with that arrow representing the yields. We could also say that same reaction in a sentence. So methane reacts with oxygen gas to form or to yield carbon dioxide and water vapor. We could even show a picture or a particulate representation of that, where this first molecule is our 1 methane. We have 2 oxygen molecules there. The 1 CO2 that we're forming and 2 water molecules are represented there as well. In that chemical reaction, we know we have the 2 parts, reactants, the things we start with, yield to form the products, which is our new substance. We see a lot of these different symbols throughout there. So again, that arrow is we yield or we form. Our SLG and AQ that you see in the parentheses are our different states of matter. So solid, liquid, gas. AQ is aqueous, which means that substance has been dissolved in water. Sometimes we'll also see things above the arrow. If we see the word heat or a delta, that little triangle that we see there, that means that we heated our reactants. If you see a chemical formula, that's the formula of any catalyst that might have been used to make that reaction go faster. In that chemical reaction, atoms are not created or destroyed. Atoms are never created or destroyed. They simply get rearranged and turned into new substances. If we do not lose or make any new atoms, mass is conserved. So that is a law of conservation of mass. So again, in that chemical reaction, reactant bonds are going to be broken. Atoms get rearranged. We make new bonds in the products. Because we're just taking the same atoms and rearranging them, mass of reactants equals mass of all products. Due to the law of conservation of mass, we have to balance chemical equation. We have to make sure that the equations we write are not randomly creating or destroying atoms. That we have the same number of atoms of each element on both sides of our chemical reaction. When we are writing balanced chemical equations, if we have a word equation, we must first translate that into a formula equation by writing our formulas from all of our chemical names. We do want to make sure we're following our nomenclature rules correctly, because if you end up with an incorrect formula for one of the substances in the reaction, it might get a little difficult to balance. So we first want to make sure we get out those formulas right. So a couple little reminders on nomenclature. If you see prefixes in a substance, it's covalent. Those prefixes tell you how many of each atom you have in there. Ionic compounds contain a metal and a non-metal. Maybe you'll see your polyatomics, but we're going to need to balance out the charges to make our compound neutral, or the charge equal to 0. Another method you may have learned to do that is crisscrossing. We also don't want to forget about our diatomic elements. So Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. If they are alone, so not bonded to another element, they get that little 2. So it would be like nitrogen gas would be the name that we would see to designate that as N2. If we have like sodium chloride though, NaCl, well that chlorine's not alone, it's bonded to another element. So it's not diatomic in that case. It gets just one of them to balance out that charge with the sodium. Once we have those correct formulas, we're going to balance one atom at a time by writing coefficients in front of the compound. We cannot ever change the subscripts in a compound because that will change the identity of that chemical. There is kind of a best order that works most of the time for balancing. And that best order is generally going to be your metals or your cations, your nonmetals or your anions, or any polyatomic ions you might have in there, and then save hydrogen and oxygen for last. When it comes to those polyatomic ions, they can be treated as a single unit if they stay together on both sides. So for example, if you have nitrate or NO3 grouping of atoms on your reactant side and your product side, we can treat it as one single thing. If we have CH and O, so if it's a combustion reaction, we want to balance CH and O in that order. Lastly, we need to make sure that our coefficients are in the smallest whole number ratio or reduce them down. So if you ended up with coefficients of like 242, we would want to reduce that down to 121. You have a couple equations to try and balance here. I recommend testing out balancing on your own at first, see what you recall, then when you're done, continue the video to check your work. So checking out what we have here on number 1, if you started with balancing iron, you might have found that your oxygens did not quite work out, so we had to make them both 6 and go back and correct that iron, so we end up with 4 irons on both sides. So if we take a look here, we have 4 irons. Remember, coefficients times subscript gives us 4 irons. 3 times 2 is 6 oxygens, and 6 oxygens on our reactant and product side. On number 2 and 3, they were both those CHO combustion ones, so we wanted to balance in that CHO order. We do want to always be careful about our oxygen since they're in 2 different places on that product side. Over here we have 4 plus 3 times 2, 6 oxygens for a total of 10. 5 times 2 gives us 10. On number 3, if you started with CH and then O, you might have found your O's didn't work out. To remedy that, we would need to start with that 2 in front of our hydrocarbon. You can also evaluate a combustion reaction to see if you'll need that 2 in front before you start. If you take that number of hydrogens divided by 2 and you get an odd number, we can just go ahead and start with a 2 in front of our hydrocarbon, and that'll make things a little bit easier. Again, don't forget to be counting both sets of oxygen over there to balance those guys. On 4 and 5, another couple that I suggest you try it on your own, but here we are taking word equations and we want to write our balanced chemical equation. So we're going to have to use our nomenclature rules first to get our reactants and products. Once we have those correct formulas, we'll go back and balance. So take a couple minutes to try those out on your own. Resume the video when you're ready to check. In number 4, the first compound we encounter is our lead 2 nitrate, and that is reacting with our sodium hydroxide. That lead 2 nitrate formula we see there, we crisscross. It tells us that both reactants are aqueous. Our formula for sodium hydroxide is going to be NaOH. As we continue reading, we produce aqueous lead 2 hydroxide and one other compound. So lead 2 hydroxide is going to be PbOH2. Again, it tells us it is aqueous, so we got that little AQ after it. We need to figure out what our other compound is. Well, we've already used the lead and the hydroxide, so that leaves sodium and nitrate to form our last compound here. Once we have all of our chemical formulas, we can go and balance. We need 2 hydroxides and 2 nitrates on both sides, and doing that gets us 2 sodiums on both sides. Looking at number 5, we have a aqueous reaction of hydrochloric acid and potassium sulfite. These react to form liquid water, sulfur dioxide, and aqueous potassium chloride. I check this out, I see that my hydrogens and my potassiums are unbalanced. When I go and fix the potassium, that's also going to give me 2 chlorines on my product side. To fix those 2 chlorines and 2 hydrogens on the product, we can stick a 2 in front of that HCl. So there you have it. Hopefully you're feeling pretty good about balancing chemicals equations, but before you move on to using them in stoichiometry.